Okay, so welcome to the ninth class on this electromagnetic theory. And in the last class, we had discussed about transmission lines, and we saw that while there can be lumped circuits where the transmission lines do not play any role, but there can be situations where, depending on the wavelength or the frequency of the signal and the length of our transmission lines or the dimensions, there can be situations where the transmission lines do play a role. And in those cases, one can estimate the effect of the transmission lines in terms of certain distributed parameters, right? Which includes R, C, G, and L. So in today's class, what we'll try to do is we'll try to get, you know, we'll try to see how graphically one can use Smith charts to estimate reactances, uh, standing wave ratios, or find out what could be the matching parameters for a circuit. Okay, so we'll try to learn about Smith charts and we'll also talk about impedance matching. Okay, so what is Smith chart? It's basically a graphical plot of normalized resistance and reactance in reflection coefficient plane. Now, two things are important here. One is the normalized reactance or resistance. So, normalized means normalized with respect to what? So, it will be normalized with respect to the characteristic impedance of our transmission line. So, if you remember, for every transmission lines, there was a characteristic impedance which we denoted as Z naught, right? So, here, this will be a graphical plot of resistances or reactances, which will be normalized with respect to the characteristic impedance of our transmission line. And now it will be plotted in a reflection coefficient plane. Now, what do we mean by reflection coefficient plane? So we know that if there is if the impedances do not match exactly, there is a reflection that happens, right? So one can get an estimate of the reflection coefficient, and this is how it's related to the load impedance and the characteristic impedance. So that means now if our load is a complex quantity, our reflection coefficient can be a complex quantity. Okay, so because it's a complex quantity, it can be plotted in a complex plane. So that makes the reflection coefficient plane. So that means any point in the reflection coefficient plane corresponds to a value of the reflection coefficient, which is again linked to a value of the load impedance. Okay. Now, what do we do with it? So with this, it's a graphical representation which would allow us to find reactances, reflection coefficients, design matching networks, determine standing wave ratios, and so on. And this becomes very useful to have a qualitative understanding, especially when we are trying to design some RF or microwave circuits. Okay, so that's where these things become useful. So now, this is how a typical Smith chart looks like. So we'll see how mathematically each of these things are related to. But if we just look at a Smith chart, here the upper half, all points in the upper half corresponds to some inductance. Okay, each points has some inductance associated with it, while the lower half has capacitance associated with it. So one way of understanding this is, so when you write an inductive load, we write it as J omega L, right? While in case of capacitance, it's 1 by omega C. So because of that, the lower half corresponds to capacitive reactance, while the upper part corresponds to inductive reactance. And this line here corresponds to a purely resistive load. Okay, the line, the straight line in the middle, in the diameter basically. And here, each of these circles, you can see many circles, right? So each of these circles correspond to constant resistances. Why is it so? We can also get there mathematically, and we'll do it in some time. But just by looking at it, so all these circles correspond to constant resistance values, and all of these arcs, you can see these arcs, right? So these arcs correspond to some bigger circles, right? These are parts of a bigger circle, which are called the X circles. Okay. And in a Smith chart, when we are talking about reactances, here, as the radius of the circles decrease, the resistances increases. So while this point corresponds to our open circuit where the reactance resistance is maximum, infinity, here this point corresponds to a zero resistance or a short circuit. Okay. So now how do we understand this mathematically? So when we write the normalized reactance, that means it's normalized with respect to the characteristic impedance of our transmission line. So that means if now, if your load has a resistive part and a reactance part, that means you can normalize it by dividing it with respect to R naught. So you get something like this. So you have a real part and you have an imaginary part, right? And this is how the load and the characteristic impedance is related to the uh, reflection coefficient. So that means the reflection coefficient can now have a real part and an imaginary part. And this is how it can be related to our normalized uh, impedances, right? So you can also revert it back and write ZL in terms of the reflection coefficient. Okay. So now, if you write the reflection coefficient as the modulus into e to the power j theta r. So here this is the argument, this is the modulus, just writing the complex quantity. Okay. So that means you can break it like if you expand and write it and try to separate out the real and the imaginary part, you would get something like this. Well, this part will be your real part and this will be your imaginary part. Right. So now what you can do is if you just look at this x equation that you get here and try to rewrite it, okay, just starting with this equation. If you rewrite it, you would get an equation like this. Okay, so that means this is the equation of a circle now. Okay, and here the center of the circles are given by r by 1 plus r comma 0, right here. So this is the reflection coefficient plane where the x-axis can be is noted by tau r, while the y-axis is given as uh, with the imaginary part. Okay, so and from here you can find the centers of our circle. So you can see that the centers always lie on the x-axis, right? And it is given as r by 1 plus r comma 0. Okay, so the centers of all our circles lie on the tower line or axis. And here you can see that if you put r equal to 0, right? So here if you put r equal to 0, that gives you a circle of unit radius. Okay, and it's centered at the origin and it's the largest. So that means this largest circle that you can see here corresponds to the r equal to 0 circle. Okay, and as you increase r, your radius decreases, right? So that means the arc circles become progressively smaller as r increases from 0 to infinity. And at this end, so if here, when you put r tending to infinity, you can see that this term will tend towards 1. R by 1 plus r will tend towards 1. So that means this term here corresponds to 1 comma 0 point. Okay. And all our circles pass through this point, as you can see, right? So all our circles pass through 1 comma 0 point, and this is our open circuit point, while this corresponds to our short circuit point. So this is for the constant R circles. And now, if we just look at this part, right, the imaginary part, we can get a similar expression, which would be something like this. So this is again an equation of a circle. And here you can see that the centers lie in 1 comma 1 by x, 1 comma 1 by x, right? So that means the centers of all x circles lie on the tower equal to 1 line. Okay. So that means this line, right? If you draw a line like this, which would correspond to the tau r equal to 1 line. So all the centers, sorry, what am I saying? Yeah, yes. So this is the tau r equal to 1 comma 0 point. So now all the circles, if you draw a vertical line here, that would correspond to tau r equal to 1 line, and all the circles, this arcs, if you draw the complete circle, their centers will lie at the tau equal to 1 line. Okay. And for x greater than 0, it's the inductive reactance, while less than 0 corresponds to the capacitive part. Okay. Now the x equal to 0. So if you put x equal to 0, what happens? So that means you get back this line, right? So that is the purely resistive load line. Okay. And again, as you increase x, the radius decreases. So as you go to smaller circles, that corresponds to more reactive loads. Okay. And all x circles pass through tau r equal to 1 and tau I equal to 0 point, which is this point. Okay. So these are the constant x circles. So now that means any point on this circle or any point, basically any point here would correspond to some reactance. Okay. So that means we can try to point and see how one can represent a reactance in the Smith chart. Okay. So suppose if you have a reactance which is given as 1 plus J1, that means now what it means is the R part, that is the resistive part, corresponds to 1. So you can see where, in this line where you have 1. So this is your 1. So that means the entire circle, this circle corresponds to your R equal to 1 circle, right? Now, in this circle, where will it be, right? So that would be again determined by the imaginary part. Now, here it is written Ji. That means now you have to consider this arcs and see where it is 1. So again, this corresponds to the reactive part being 1. So similarly, now you can see where these two lines meet, and this is your point. So this corresponds to this reactance. So similarly, you can have different reactances and you can plot it on the Smith chart. Okay. Now, there are certain points to remember in order to understand how to work with Smith charts, right? So if you remember, we had some circuit like this, right? So if you have the source here, okay, some generator, okay, some voltage here, you have some resistance or some reactance, some impedance here, and then there's a transmission line of some length L. Okay, the characteristic impedance is Z naught, and there is a load impedance given as ZL. And here one can take the convention that at this end your Z is L, while here Z is equal to 0. Okay, so that means here Z equal to 0 corresponds to the source, okay, and Z equal to L corresponds to the load. And one can define another term, another variable D, which is just the reverse. So here D is equal to L, okay, at the load, and D is 0 at the source. That means Z and D are related to the length of our transmission line by this relation. So Z equal to L minus D. Okay. So now we know that if you have a lossless transmission line, we know that the gamma is given as J into beta. So alpha is basically 0. And in general, you can have the voltage written like this. So you will have a incident like a forward moving wave, and you will also have a reflection coming, okay? And the ratio of the two would give you the reflection coefficient, right? And in general, this will be a complex quantity, so it will have a modulus and a phase term or argument term. So now at any particular Z, so at any particular location in the transmission line, one can write the reflection coefficient by this relation, right? Basically, you are doing a ratio of the two, V0 minus e to the power gamma Z by V0 plus e to the power minus gamma Z. So you get this. So here this term corresponds to this ratio, right? Into e to the power 2 gamma Z. Now you can write Z in terms of L and D. And this is what you will get, considering that now your gamma has both alpha and beta. Later, if it is a lossless case, you can put alpha to 0. Okay. So that means you can expand it and you would get something like this. So here you have this terms which depends on D. And what is D? D basically tells you how far you are from the load in the transmission line, right? So that means there is a dependence on how far you go from the load. And these are the terms which take care of that. Okay. And while this entire term, you can consider it to be some uh, factor given as tau L. Okay. So now what you can do is this term here, you can see depends on D, while this like you can see here it's the subscript is capital here L, here it's small l. So basically you can write a relation between the two, but both of this do not differ in their magnitude, right? You just have this extra phases coming in, where if you find the magnitude will be the same. So that means you can basically write the reflection coefficient at any particular D location on the transmission line by this relation. Okay. So that means as you move, so if you now start at the load, there the transmission reflection coefficient is given by this relation, which has some phase phi l. At a later point, anywhere in the transmission line at a distance d from the load, your reflection coefficient will have an extra phase, which would be given as minus 2 beta d. Okay. And minus denotes that you are moving clockwise. Okay. As you can see. So basically, you would have to move clockwise so as to reduce the amplitude. Okay. So that means as you go away from the load, you acquire an extra phase change of 2 beta d. While beta is given as 2 pi by lambda, where lambda is your wavelength of your signal. So now what you can say is that this is the total phase change. So if you put d equal to lambda by 2, you get a phase change of 2 pi. That means if one moves by a length of lambda by 2, we get to the same point on the reflection coefficient. Why? Because that would give you the same value, right? In the reflection coefficient, each point corresponds to a tau value, right? So that means because it would be a phase change of 2 pi, you would get back to the same point. Okay. And we would see how we characterize or how we calibrate this distance with respect to the WTG scale, which is the wavelength towards generator scale. Okay. And it's important to note that while you move, your reflection coefficient magnitude does not change. Okay. So if you draw a circle of a constant radius starting from a particular impedance value, that would give you the constant ASWR circle. Okay. Because along that circle, your reflection coefficient and therefore the SWR won't change. Okay. Now, in case alpha is not equal to 0, then what would happen? Then your amplitude will gradually decrease, right? Your voltage signals will decrease. So that means in that case, you won't get a circle, rather you would get a spiral. Okay. And we would see later how one can directly look at the Smith chart and get an idea about the SWR, which would be directly given as the maximum of the resistance that is there on your transmission line and also the minimum value. So we'll see this with the examples, and I think that would be clear. Okay. So now, based on what we have discussed till now, let us try to answer these questions. These are little conceptual questions which will make our concepts clear. So here it says that Smith chart is a graphical indication of the impedance of a transmission line and of the corresponding reflection coefficient as one moves along the line. So this is true. This is the basic definition of a Smith chart, right? Now the second question says that lambda distance on the line corresponds to a 720-degree movement on the Smith chart. So is this statement correct? So in order to understand that, we have to again consider the, the phase part that we discussed, right? So we saw that d equal to lambda by 2 corresponds to a phase change of 2 pi, that is 360 degrees. So that means lambda would correspond to a 720 phase change, right? So that means this point is correct. Now, what is the third point telling us? The third point is telling us that the admittance chart can be obtained by shifting each and every point on the impedance chart by 90 degrees. Is this statement correct or not? So here we have to understand how do we define admittance, right? So it would be given as 1 by the the uh, the reactance. Okay, so that means if in a react in an impedance, when you represent the Smith chart in terms of impedances, there we know that this point corresponds to the short circuit, while this point corresponds to the open circuit, right? So now if it is reverse of that, which is your, so now if you are talking about admittance, it would be reversed. So there, this point will correspond to your short circuit point, while this will correspond to your open circuit point. So that means you have a shift from here to here, which corresponds, as you can graphically see, which corresponds to a phase change of pi, right? Not 90, but 180. So that means here this is not correct. It should be 180 degree. Okay. Now, again, this is another statement which is very important, which says that counterclockwise movement on the chart corresponds to moving towards the generator. Is this a correct statement or not? So how do we understand that? So we saw that as you start from the load and you move towards the generator, right? So as your D, as you approach towards the generator, we acquire a phase of minus 2 beta D, and that means a clockwise rotation, right? So that means as you go towards the generator, because your phase decreases, so that means it's a clockwise rotation. This answer is wrong, right? So in while talking about Smith charts, whenever we are talking about moving towards the generator, we will be moving clockwise, not counterclockwise. So in this statement, for this question, it's only 1 and 2 which is correct, right? 3 and 4 is not correct. Okay. Now here it says that when the load impedance is equal to the characteristic impedance of the transmission lines, then the reflection coefficient and the standing wave ratios are what? So this we know, right? So whenever the load impedance matches with the characteristic impedance, so there is impedance matching, that means there should not be any reflection, right? So that means the reflection coefficient should go to 0. And if you remember the relation between reflection coefficient and standing wave ratio, so basically standing wave ratio means you have a forward moving wave and then a backward moving wave comes in. So here the reflection coefficient goes to 0. So that means in this case, the standing wave ratio would turn out to be 1, right? So if you remember the relation, this is how it looks like, right? This is how the standing wave ratio is related to the reflection coefficient. So if your reflection coefficient is 0, your standing wave ratio should be 1. So based on this, there can be different kinds of questions which are very straightforward to answer. So one such question in the last year's assignment was something like this. So it says that a transmission line is terminated using a purely capacitive load, and this is how the load is. And it is said that the VSWR, that is the standing wave ratio, is 1. What is the impedance of the transmission line? So because the standing wave ratio is 1, this is directly telling you that the reflection coefficient must be 0. That means there is no reflection. And because there is no reflection, this hints at the fact that the impedance must have matched, right? So that means the impedance of your load should match with your transmission line. So that means if the impedance here is minus J10 ohm, then here also the transmission should have the same impedance, which is again minus 10J, right? So this could be how, very straightforward questions can come from this concept. Okay. Now here it says that this is another question which says that the impedance is Z equal to Jx for all x in the range minus infinity to infinity. How do they map to the Smith chart, right? And these are the different options. So how do we answer this question? So here, as you can see, the impedance do not have any resistance part, right? Any real part is not there, right? So that means if we if we compare with what we have, like the last expression the first expression that we discussed, here this is 0, right? So that means now you can put R going to 0. So if your R goes to 0 and if you put R equal to 0, what will you get? This term will go away and this will be 1, right? So basically you would get a expression like this, right? Tau R square plus tau I square equal to 1. So now this is very clear. This is an equation of a circle in the reflection coefficient plane with a radius of 1 and the center at 0, 0, right? So you can draw the circle. So now you can see which one matches. So you can see it matches with the first option, which says that a circle of radius 1 with center at 0, 0. This is with respect to the reflection coefficient plane, right? Because here your x corresponds to tau r and y corresponds to tau I. Okay, so this is how one can relate impedances to points on the Smith chart. Now, impedance characteristics on a Smith chart repeat after a distance of. So this is a straightforward question we just discussed. We saw that lambda by 2 corresponds to a 2 pi phase, right? So that means the impedance would come back to the same point. We would get the same point if we travel a distance of lambda by 2. So the answer should be lambda by 2. Now, this is another question which is mainly based on what we have already discussed. It does not take into account, you do not need Smith charts for that, but this was one such question in the last year's assignment. And this is just based on the idea of, impedance matching. Okay. And basically considering the fact that you would have some reflection if the impedances do not match. And if there is a reflection, your your voltages will change accordingly. Okay. So let us try to see how to answer this question. So here you see that you have a the generator has some resistance. Okay. So at the source, okay, and there's a switch here. You know the characteristic impedance of your transmission line. You know the load impedance. Okay. So it says that what is, so at when the switch closes, what is the voltage V1 plus, right? So basically, what is the incident voltage at this end? This is what you're trying to find, right? So this is very similar to what we had discussed in previous, I think last class or the class before. So you have some 50 ohm here, and you have the impedance, the characteristic impedance given as 50, and the voltage here is 10. So, yes, Jayanta, do you have any question?
Oh, sir.
Yes. Hello. Okay. So, so that means here you have 10, right? So you have a 10 volt here, and here it is 50 ohm. Here again at the start, right? At the source, here again you have 50 ohm. Just ignore my handwriting. So this is 50 ohm, right? And here also you have 50 ohm. That means there'll be a voltage division that would happen, right? So if you see what would be the voltage drop, so there would be a 5 volt voltage drop here and a 5 volt voltage drop here. So you can say right away that V1 plus should be 5 volt, right? If it was some other ratio based on the ratio of your RG and Z naught, you can say in some other question, you can say what your V1 plus should be like. Now the question says, find the reflected current from load. Okay. So reflected current means the voltage, there'll be a transmission along the transmission line. Because Z naught does not match with RL, there will be a reflection, right? And that reflection, so that will correspond to some reflection coefficient. So you know Z naught, you know RL. You can try to find what your reflection coefficient will be, right? By using this relation. This is the relation, right? This ZL minus Z naught by ZL plus Z naught, right? The base, the general, I don't know, I just want to show you the, just to recall, I don't know where it is. Yeah. So this is the relation, right? So you know ZL, the load, you know the characteristic impedance. So you can try to find what is the reflection coefficient for your circuit, right? So if you do that, what it will be? 25 minus 50 by 25 plus 50. So it should be minus 1 by 3, right? So that will be your reflection coefficient. So now that you know reflection coefficient, if your incident voltage is 5, right? And this is your reflection coefficient. Can you tell me what the amplitude of the reflected voltage will be? The incident voltage is 5. The reflection coefficient is minus 1 by 3.
5 into minus 1 by 3.
Right. So it should be minus 5 by 3. Right. And the minus just signifies that it is a reflected wave. Right. So that means the voltage of your reflected uh, the reflected voltage will be 5 by 3, right? The question says, find the reflected current from load. So it is said I1 minus. So it is important to note this 1 signifies what is the value at the source, right? At the generator end, not at the load end. So now you know the voltage. Okay, so this is the V minus. Okay, and you know the impedance at the at the incident site, and that is given as Z naught, that is 50. So that means now if you use the relation V is equal to IR, so I is equal to V by R, V is given as 5 by 3, and R is Z0, which is 50. So can you tell me what the reflected current will be?
1 by
Basically,
30.
yeah, yeah,
1 by 30.
I just lost you.
1 by 30.
So
33.3 milliampere.
33.3.
yeah, right. 5 by 3 divided by 50, right? So then this should be your answer. Now the question says, now we are going to the load side. Okay. So it says, what is the steady voltage at the load and what is the current at the load? So your incident voltage was 5. Out of that, 5 by 3 has been reflected, right? So what is the voltage that reaches your load? That should be nothing but 5 minus 5 by 3, right? That should be the voltage at the load, right? So if you do 5 minus 5 by 3, you would get the voltage at the load. Now, once you have the voltage at the load, again, you can use the relation V is equal to IR. Now you know the resistance at the load, which is 25, right? So using that, you can try to find the current at the load. So can you tell me what the answer will be?
3.3 volt, 0.13 amps.
Correct.
0.13 amps.
This one, right? Yes.
Yes, ma'am.
Yeah.
Now,
Okay.
for the first question, it is 5 volt.
Yes, because you have 50 ohm here and you also have 50 ohm here, right? Z0 is 50. So your 10 volt gets divided between the two. Okay. If it was some
It's
other,
a 5.
yes, it should be 5. If it is some other, if the ratio is different, suppose if it was 150, so then it would be divided accordingly, like a voltage divider, right? Okay. So now let us come to again Smith chart problems. So we know that we can represent impedances on the Smith chart. Now let us see how do we solve questions like, if the impedance at the source is this much, what would be the impedance on the load side? How far will it be? What would be the length of the transmission lines and so on graphically, right? So here the question says, I just lost one second. Yeah. So here the question says that, this is the characteristic impedance. This is the length of your transmission line and this is your ZL at the load. Okay. The question says that how do we represent the normalized impedance? So the first thing that one should do or one should know how to do is to represent the normalized impedance, right? So you normalize it with respect to the characteristic impedance of your circuit. So if this is your ZL, ZL by Z0 will be the normalized impedance. And now what you have is 0.1 plus J into 0.5. So you can locate, basically, if you have such a Smith chart, you would see where the R, this is the real part. So while where the R will be equal to 0.1, right? And where in this arcs, this look at this points and see where it corresponds to 0.5. So in that way, you can locate the normalized load impedance, right? So this is how you locate it. Now, once you have located it, it says, what is the impedance at L equal to 0.1 lambda? Basically, what is the impedance at the generator side, right? So how do you do it? So first we extend this, extend this line such that we get the, so this scales tailors about the location with respect to in terms of distance, okay, and the distance is with respect to wavelength, and it tells us where we are with respect to the generator, right? So wherever it cuts, that gives us a distance, okay. So here suppose this is 0.074 in the WTG line, okay. Now you have to move 0.1 lambda distance. And because we are moving towards the generator, we know the load, we are moving towards the generator, we will move clockwise. Okay. So now if you move clockwise, we would get to this point, right? Here, extend it further. And here, starting from this we know the R value, right? So from this point, what we can do is basically we can draw a circle, and that circle will correspond to, so any point on this circle will correspond to the same reflection coefficient value, right? This is called the SWR circle. Okay. So now when you extend this line, it will cut at one point. So this point will correspond to your normalized impedance at a distance of 0.1 lambda from your load point, right? So this is your answer. So now if the question says what is the impedance, this is your normalized impedance. So you have to multiply it with your characteristic impedance given in your question. Okay. So this is then the impedance at the generator end. Okay. Now the question says what is the VSWR on the line. So basically VSWR corresponds to the maximum. It comes from the ratio of the reflection coefficients, right? And there it tells you about the maximum resistance that can be present in the transmission line. Now we know that as the radiuses of the circle, as the radii decreases, the resistances increase, right? So this circle, wherever it cuts, so it would cut at 2 points, right? Here, if you extend it further, if you make a complete circle, it will cut somewhere here and it will also cut somewhere here. And this line is the purely resistive line. So wherever it cuts in, at the smaller radii side, that would correspond to the maximum resistance that is present on your transmission line, right? And that point will correspond to your VSWR. Okay, so in principle, what you can do is you can measure this distance and there is a scale provided. So from here also you can find the value of your SWR. Okay, so that's how you do it graphically. Now, what is the reflection coefficient, right? So we know that this circle, so the radius of the circle is a constant value and that corresponds to the reflection coefficient, right? So what you can do is you can measure this distance. So you can use a protractor or a scale and measure this distance. And based on the scale that is provided here, you can see what is the magnitude of your reflection coefficient. And how do you find the angle? So if you extend it further, this scale here that you see gives you the angle. Okay. The argument of the reflection coefficient. So here you can see it matches with some 126 degree 0.5, 126.5 degree. So that is your argument. So that means at the load, your reflection coefficient is given as 0.855 e to the power j 126.5. Now, what is the reflection coefficient at the generator side? So again, as you know, the entire circle corresponds to the same modulus. So as we just discussed, right? So when we move from the load to the generator, the magnitude of the reflection coefficient does not change. So that means the magnitude would be the same. Only the phase will decrease, right? So that again, if you extend it further from the scale, you can get the angle, right? So that means at the source, at the generator side, this would be your reflection coefficient. So that's how one can use the Smith charts graphically. Okay. So let us look at some more examples. So this is another question. Again here, the Z0 is given, L is given, ZL is given. So here Z0 is 1. That means whatever you will be getting will actually be your impedance, right? It's already normalized because Z0 is 1. So here, what you do, you first locate the normalized impedance, load impedance. So once you locate it, it says what is Z at some distance lambda by 4. So you're moving from the load towards the generator. So move clockwise, right? So you extend it further to get the location. So this is your wavelengths towards generator scale. So this will give you a value. As you can see here, it's 0.467. So this corresponds to a particular distance. Okay. And now you have to move clockwise by 0.25 lambda. And you get to this point. Extend it further and see where it cuts the SWR circle. And this gives you the impedance at that particular distance. Okay. So that is your Z. Now what is VSWR? So again, you see where it cuts in this line corresponding to the maximum resistance that is there in your transmission line, and match this distance with the scale to get the VSWR. Okay. how far from the load is the first voltage minimum? Now, when will the voltage be minimum? So the voltage minimum will correspond to the location of minimum resistance, like V is equal to IR. So that means if you find the location of the minimum resistance in your transmission line, that would be the location of the minimum voltage. And what will be the minimum resistance? So you know that, this is the purely resistive line. This is the maximum voltage and this is the minimum voltage. The resistance increases as we go inwards. So this point corresponds to the minimum voltage point. So the question says, how far from the load is the first voltage minimum? So basically, we have to find this angle difference, right? So you know this point. You can again look at the value of the distance, like look at the scale here and find the difference to see what is the distance that has to be covered once you move from the load towards the minimum voltage point. Similarly, if you were asked to find the position of the maximum voltage, then you have to find this distance, right? So then the entire distance from here to here has to be covered. Okay, so that will be nothing but 0.033 plus this value, right? So if you are asked to find the position of maximum resistance. Okay, so that's how you make use of the Smith chart. Now, in certain questions, there could be questions where the length is not provided in, like it's provided in, normal units, right? Centimeter or meter or something like that. So in that case, you have to convert it first in terms of the wavelength of your signal. So here you can see that the frequency of your signal is given as 3 gigahertz. So you can use this relation to find the wavelength. And then based on the wavelength, you can convert this length in terms of the wavelength, right? So once you get that, it becomes a similar kind of question. Okay. So again, here Z0 is given, ZL is given. So you can try to locate the normalized load. It turns out to be somewhere here. Extend it further. Find the line impedance 2.5 centimeter from the load. So this 2.5 centimeter, when you find lambda, you see that you have, so now you know how much you have to go with respect to lambda, right? So it's 0.25 times lambda. So again, go clockwise. You go to this point, extend it further to the SWR circle. So this gives you the impedance at a distance of 2.5 centimeter from the load. Okay. This is again the VSWR where it cuts the resistance line. Okay. This is the VSWR. You can measure it using this scale that you have, or you can measure it directly. Okay. So in certain questions, you can have the other way around. Okay. Where your, so initially in the last few questions, what was happening is your ZL was given. You had to find the resistance impedance at the source, right, at the generator side. Now the other way around can happen where your impedance at the generator side is given. You have to find the load impedance. Okay, and the distance or the length of your transmission line is provided. So here you use another scale, which is called the wavelength towards load scale. Okay, so only difference is in this scale, you have to move counterclockwise. Basically, it comes from the same fact that when we discussed before, we saw that when we moved from the load towards the generator, we had this minus J2 beta D phase coming. So now when you move from generator towards load, you will have addition of phase. That means you have to move counterclockwise so that the argument increases. Okay. So in the wavelength towards generator scale, you move clockwise. In the wavelength towards load scale, you move counterclockwise. So now here it says that this is your impedance at the generator. This is the length. What is the normalized receiving or load impedance? Right. So first you locate the impedance at the generator. Extend it further. Now you have to look into the wavelength towards load scale. This will again give you a distance. Now move counterclockwise, right? So move counterclockwise by this distance, 3 lambda by 8, to get to this point. Extend it further inwards to find the load impedance. which is at a distance of 3 lambda by 8, right? Now, this is the first part of the question. Now it says, what is the distance from the load to the first voltage minimum? So here you again have to find the distance from the load to the first voltage minimum, which is along this line, right? Wherever it cuts at the line. So this point. So now what it's important to, like, once you get used to using Smith chart, you would see this point corresponds to the, if you look at the wavelength towards load scale, this corresponds to the 0 point, right? And this, the load is at 0.064 lambda. That means you have to find the distance between this point and this point, which is nothing but 0.064 itself, because this point is nothing but 0 on the wavelength towards load scale. Okay, so that's why you can directly, once you find it, you can directly say that from the V minimum point, the distance from the load is given as 0.064 lambda. Okay, now what length of open circuited line could be used to replace ZL? So basically, this is the ZL that you get at this length. Okay, and now the question says, if you want to replace this load with an open circuit line, that means now your impedance would be infinite, right? So what should be the length of the open circuit line? That's what you have to find. So basically, from the position of the ZL, we want to move towards a new load, okay? And which corresponds to this point, right? So now what you can do is you can locate this point on the wavelength towards load scale, and that would correspond to 0.25, right? So if you look at the scale, here you have 0.25. So this point corresponds to 0.25 on the wavelength towards load scale, okay? And we know that the position of your ZL is at a 0.064 lambda from the origin, or the zero of the wavelength towards load scale. That means how far will you have to move? You have to move this much, right? From here to here, right? And that will be nothing but 0.25 minus 0.064, which is 0.186 lambda. So that means if you have a okay, of an open circuit line, then that would correspond to the same, uh, that would give you the same, basically the same analogous form of your circuit. Okay, so that would replace ZL. So ZL at this distance is equivalent to having an open circuit line of 0.186 lambda with the impedance given as infinity because it's open circuit. Okay. Now talking about impedance matching. So we know that when there is impedance matching, what happens? There is no reflection, right? So that means if you have some source, source impedance or some impedance at the generator end, and if there is some load, maximum power transfer. So if you try to, write it in terms of both resistive and reactive loads and try to find out, you would see that the maximum power is transmitted when ZL is the complex conjugate of your um, generator impedance, right? So there can be direct questions which just makes use of this. So suppose your impedance on the generator side is given and you are said that what should be the load so that the maximum power transfer happens. So you just have to do the complex conjugate of your um, load at the generator end. Okay. But that is not the other way around. This is something you have to remember. So if it is other way around, so if your ZL is provided and it is said what should be the ZG. So in most cases we put ZG to 0. Okay. So now the question is that in a normal in a normal circuit, we know that there has to be a matching on the two sides. One is the load side and another is the source side, because you would have some resistance on the source side. There will be a characteristic impedance of your transmission line, and then there will be a load, right? So at the load end, your ZL should match with Z0. And again, at the source end, your ZG should again match with your Z0, right? So there should be a matching on the two sides. And if that matching is done, then that corresponds to the impedance matched condition, right? And how can one achieve this kind of a matching? So there can be many ways. One is a transformer matching. So basically what you do is you have a transformer somewhere here so as to balance or equalize the voltages, right? So that is one way. Another is to use a lumped element matching. That means you have a combination of L and C such that the effective impedance that you see equalizes on the two sides. So if your Z0 and ZL does not match, you can put a combination of L and C so that the effective impedance on the load side matches with Z0. So that is the lumped element matching. Another is the quarter wave transformer matching. So here, if you remember the questions that we were solving in the previous classes, so we had this, cascaded kind of circuits, right? Where the load for one was actually the incident voltage for the incident impedance for the other, right? So there, that means you can have such kind of, you can add quarter wave transformers where the Z in and your load and the reactive characteristic impedances are related by this relation. So basically, if your Zg is provided, okay, and your ZL is known, what should be your Z naught? So based on the wavelength of the signal that you want to transmit. So suppose you know Zg, you know ZL, you can tell what Z naught will be, right? So in that case, Z naught will be nothing but root over of Zg into ZL, right? And that value, how much the length should be, for that depends on the wavelength. It should be a lambda by 4 length of transmission line. So lambda will correspond to the signal wavelength. So this kind of transformers do not work good for cases where you have a range of wavelengths being transmitted. If it is a very wavelength specific thing, then this becomes very useful. Okay. And another is the stub matching. So in stub matching, basically what you are trying to do is you are trying to add a stub. So in general, you can have multiple stubs, okay, in series or in parallel. But what is the simplest case is to add a single stub in parallel, okay, to your circuit. So if you have some circuit like this, what you want is you want ZL to match with Z0, and you also want your ZG to match with Z0, right? That is the matching that you want to achieve. And this is the length of your transmission line. So here in parallel to this transmission line, you can add a stub, okay? Now this stub can be a short circuited line, basically, or it can have some impedance based on whatever you choose. Generally, if you can choose a short circuited line in parallel to this transmission line such that the impedances match. So how this is done is basically you, because we are talking about, uh, you know, because the stub is connected in parallel, we move from the impedance to admittance. Okay. So if you have some impedance, so basically if you have a, if you have a Smith chart, and if at some location, so suppose this is your impedance, if you want to write it in terms of admittance, you have to move by 180 degree, right? So if you draw a 180 degree line, so if you move by 180 degree, you would end up somewhere here, right? So that would correspond to your admittance corresponding to this reactance, right? So now what you have to do in this kind of questions is you have to write your all the reactive, all the impedance terms in terms of admittances, okay? So ZL can be written in terms of some YL, which is admittance, okay? Again, your Z0 can be written in terms of minus Y naught, which corresponds to some admittance. Okay, that is the characteristic admittance of your transmission line. And now what you can do graphically, how it is done is, so you first locate YL. Okay, so basically in this circuit, you would have YL somewhere here, right? Corresponding to this, you can have a YL. And this circle would be nothing but your SWR circle, right? Now you would see where this circle would intersect, where this circle would intersect with the unit circle. Unit circle corresponds to the circle where the resistance is 1. So that means there, any point on the unit circle will have a form of admittance given as 1 plus JB. So what what you are actually doing is you are saying that you have some load, okay? You have a particular length of your transmission line such that at this end, your admittance looks like 1 plus JB, and you want to find this length. So this you can do, right? What you can do is you can locate this in the Smith chart and then see where this SWR circle cuts the unit circle, okay? And that point will correspond to some 1 plus JB turn. So if you mark this as a point A, then the distance from YL to A will give you the distance from load to stub. Basically, at that distance from the load, you need to add the stub. So if the question asks, where do you add the stub? So this distance, you can find it from the scale in the Smith chart, will give you where you should add your stub. Now, once you add the stub, what you want to get is you want the impedance on the other end to be matched, right? So basically by adding a stub in parallel, what you want to do is if this is 1 plus JB, you add a stub to it such that the resultant becomes 1 plus J0. So that means the stub impedance admittance should be minus JB. And this B will depend on this, will be related to the length of your, of how, what is the length of your stub that you are using, okay? So now once you have located the point, okay, the distance moved from YL to A, that is this length L. So once you have found that, now the question is, what is the length of the stub? So basically here you are adding at this point, suppose at this location, you are adding some short circuit stub in parallel, right? Now what should be the length of this thing? How do you find that? So there what you do is in the admittance chart. So remember now we're talking about admittance. So in the admittance chart, this point corresponds to the short circuit point. So this is your short circuit point in the admittance chart. And if you have located your A point, right, you know what is your A, which would correspond to some minus J beta, 1 plus J beta. So from that point, sorry, okay. So from that point, suppose if it is somewhere here in the outer circle, so basically along this line, if you find the distance, suppose somewhere here, if this is your point, extend it further, then this distance would give you your length of the stub. So that's how graphically one can use a stub in parallel to have impedance matching. Okay. So that's it. Any questions from your side?
Ma'am, here we have a multiple choice question paper, MCQ type question.
Okay. Okay.
How we can do this Smith chart using Smith chart and everything?
So basically, you can get Smith charts online, I think.
Ma'am,
Because, you know,
online, ma'am, in exam, end exam.
so see, actually, the fact is that I don't know how or what kind of questions, whether they'll be providing Smith charts in the question or not, because so this is like, you know, this is just
Sir, they will be providing in the exam, sir. They will be providing in the exam. So last
Okay.
time I have attended antenna.
Okay.
In that they have provided.
Okay. Okay. Because
Okay, that's fine, ma'am.
yeah, I actually don't have idea because I'm like, for my case, it's just to discuss certain typical questions so that you get an idea. That's what I am like entitled to do. If you have this kind of doubts, you can ask in that panel. But now he has
Okay.
clarified, so I think he'll get Smith charts. So that's also
Okay.
no problem.
Whenever we are just discussing the things in the discussion forum, we are not getting the response in a proper way, ma'am. We are not been responded. The last time, sirs, Praveen sirs, yeah, that is electromagnetic waves in guided and unguided medium that I have attended. In that I haven't
Actually, ma'am put her session in a muted. Finally, ma'am unmuted. That's why ma'am cannot able to hear our response. Sir. And the previous
ma'am.
session, no, it's okay. And 2 sessions back, it happened, ma'am. You muted your
me?
laptop. That's why, yes, ma'am. We asked
Oh.
several questions, but finally you noticed that your laptop sound is muted.
So you were not able to hear what I was teaching?
Your voice is clear, ma'am. We raised some questions, but
Okay.
you are not answering the questions.
Oh, no, no. Okay. Because I sometimes follow the chat, but so if these things happen, do write in the chat because I do open the chat and see sometimes because I don't know why you guys got muted.
Yes, ma'am. We also insist that you have to write it in chat, but the person who is asking question, he not write it in chat. That's why it happened.
Oh, okay, okay.
2 sessions back.
Okay, so if whoever has asked a question, if you have a question, you can again, write it and I can just go back and see what is the question and try to address it. Okay. Because I did not know because I sometimes do check the chat and I don't know how someone got muted. So, but if the question still is, if you still have the doubt, whoever it was, you can write it in the chat box or, let me know in the next class and I can just go back and check and tell you what, if I can do any help. So I'll see them. And regarding this discussion forum, so so what I have been told because this TA session is being done as a part of PMRF TA-ship. So there, what I have been told is if there's any question pertaining to the class that I am taking, I'll try to address that. Other questions, like if there's some question pertaining to, the NPTEL courses or the lectures, I am not entitled to answer there. So I think that will be answered by the TAs of that class or the professor himself. So, I don't know about that. If you have any doubt regarding what we are discussing, you can either ask me here or we can discuss in the forum. Okay.
What is the length of the VSWR circle, ma'am? It is lambda by 2, correct?
What is the length
Yes.
of the, yes.
VSW,
Because
lambda by 2.
because basically once you travel a lambda by 2 distance, you come back to the same point. It's a 2 pi phase, right? So it should be lambda
Yeah.
by 2.
Ma'am, suppose sometimes if I have that questions, if they provided some load impedance, something values 1 plus J5 means. Suppose if VSWR 1 means it should be a complex conjugate of that load impedance, correct?
If
Then only
SWR is
maximum power delivered or VSWR equal to 1, both are same.
SWR
VSWR 1 means
1 means
maximum
there
power
is,
transfer, correct?
yes. Because there is
VSWR
matching,
equal to 1.
right? SWR1 means it's a matched circuit because there the reflection becomes 0, right? SWR1 would correspond to the reflection coefficient being 0.
0. So, so the load impedance or the source impedance, it should be a complex conjugate of that other term, correct? Suppose
So
if
there are two
if you
things. So
assume 1
first is,
minus.
no, there's two things. First is if you have some on the generator side, and then there is a load. So there, this is the relation, right? This happens when you have maximum power transmitted. Okay, so this is one condition. Now, what you are saying is there is no reflection from the other end. So that means
Yes.
they are the amplitude, they are the impedance should match. So if you have, so suppose your Z0 is provided and you want to find ZL, then your ZL should be equal to Z0 at that point so that there is no reflection.
Okay. We are not supposed to combine maximum power transfer with the VSWR, correct?
Yes.
Sir, maximum power transfer at the time ZS is equal to Z0 we will be having, sir. So whenever we are having ZR is equal to Z0, at that time we will be having ZS is equal to Z0. So ZR is equal to ZS is equal to Z0. So at that time we'll have a maximum transfer of power.
Oh, it is a complex conjugate. ZL equal to ZZ.
It will be purely resistive, sir. It will be purely resistive if it is so.
No. If I am asking, suppose if I am having a capacity reactance,
inductive
or
reactance, then
inductive reactance.
it must be a complex conjugate at that time. Maximum transfer of power. But as far as transmission is concerned, Z0 must be same. Then only we can have a Z0 and ZR will be same as that of ZS. Then that
Yes,
case we will be
that is
having
that is the
maximum.
case I am asking. So
Mhm.
suppose if it is a load is a 1 plus J.2. So if a VSWR equal to 1, so
Hmm.
that time what should be the
ZS,
transmission line
ZS,
impedance?
ZS will be complex conjugate then.
Uh-huh.
No.
That's
If
why I'm
your
asking.
Z0, what is the value of Z0, sir?
That
Z0
is the
is given.
question. That is the question. What is the value of Z0?
Oh,
That is the
yeah,
impedance.
okay.
see, if your ZL is something like ZL is 1
One-
plus J,
Reflection
1 plus
coefficient
10J. So suppose your ZL is 1
reflection
plus
coefficient
10J.
0.
VSWR equal to 1.
That means
So then
reflection coefficient is 0, right? So
0.
that means
Yes.
that means Z0 should be equal to ZL.
Okay.
ZR.
Equal to that.
So 1 plus 0.2J
ZR.
only we will be having,
J.
sir. 1 plus
1 plus
0.2J
J.
only we will be having, sir.
Yes. Whoever
1 plus
you are
J.
saying, it's correct. Just let me sum up. So basically what you are telling is, if you say that your SWR is 1, that means there is no reflection. That means the characteristic impedance of your transmission line should match with the load, okay, at the load end. So that means Z0 should be equal to ZL. So if your
Okay.
ZL is 1 plus 10J, then your Z0 should also be equal to 1 plus 10J.
Okay, ma'am. That is it. Okay.
Yeah.
Thank you.
Okay. If there's no other question, let's call it a day. Thank you.
Thank you, ma'am.
Thank you.